see how this works if you have more complicated possibilities, not complicated, just more possible critical points. So fx.
Multiply that through.
Yeah, would you how would you start out this?
Me, I would not FOIL it, because pretty much to solve, anytime you know your next step is to set the derivative equal to 0, I want to leave it as factored as possible to begin with, right? So just, you know, grin and bear it. You gotta do the what's going to be involved here. Product rule. And what you really have, you could be a little more focused. I wouldn't multiply it all the way through. For this, I might multiply my x's together. Right, that's an option.
So it's y times.
So you have like y times y plus 3 times x squared minus 2x. Why does it help you out? It's a lot easier, right? You guys see that? It's not a bad suggestion. So fx, what would happen with these?
Those would both be a constant.
And they stay there. I like it. So y times y plus 3. 2x minus 2. So now, by putting my x pieces together, I don't have to do a product rule. And if I put my y pieces together, fy is going to be x times x minus 2 times 2y plus 3. Cool. So let's do this one step at a time. What you really have here, the point I want to make sure is understood, is you have a system of equations. You must find all points where both of these are true. So obviously one way to do that most directly is to solve one of them and then plug it into the other one. You have this equal to 0 and that equal to 0. You want that to both be true. So what makes the first one work? Call it A and B. Yeah, from A I get y equal to 0, y equal to negative 3, and x equal to 1. You with me? So those make the first one 0. Let's plug it into the second one and see what else makes the second one 0. So they're both 0 at the same time. So what happens when you plug y equal to 0 into the second one? What does that B equation become? Throw y equal to 0. Now let me make sure everybody's with me. We got these numbers from this equation here, right? That's how you find a critical point. You set the derivatives equal to 0. The only difference from before was derivative wasn't plural in the past. Now it's plural. Set both derivatives equal to 0. The first equation gives me these 3 possibilities. Cool? What's the second equation do if y is 0? I get 3x times x minus 2, which gives me what? X is I like it. So don't make more of this than it is. It really is just get the things that make this 0. Plug each one of them in here one at a time. Why was the other one easy? Because the answer was just one answer. And the other equation wasn't really an equation. It was a number. There wasn't anything to plug into the other one. So here I get x equals 0 or 2. Right? So what points do I have so far?
0, 0, 0, 2.
I like it. So when y is 0, I get 0 for x and I get 2 for x. So now you start to see the math involved in collecting this list of critical points. This list of candidates for local maxes and mins or saddle points. What do you make y equal to negative 3? Yeah, you just get negative 3x times x minus 2. So again, that still leads you to 0 and 2, right? So what points do we pick up there? So when y is -3, I get 0 for x and I get 2 for x. How are we doing so far? And just follow your math. Those of you who are a little messier than I am, you're gonna hate this because it's all about keeping track of what's leading to what. When y is -3, I get x is 0 or 2. 2 points there. When y is 0, I get x is 0 or 2. 2 other points there. When x is 1, what do I get here? A constant times this. Can you guys see? So that would be y equal to what?
3 halves.
Yeah, negative
3 halves.
3 halves. So my last point would be 1, negative 3 halves.
It's positive.
Got to subtract 3. Divide by 2. How are we doing so far? Is that decent? Yeah.
Doesn't that x minus 2 go to a negative 1?
Yeah, -1.
I don't care. It's equal to 0. Come on, guys. So if x is 1, this is a constant. Divide by it. So that's really my problem. Right.
But it's still there.
But I can kill it. I can divide by it. 0 eats it for lunch, right? So this, yeah, this would be 1 times -1 is -1. Divide by -1, bam. So my real problem is this then. Right, so look for that. All you want here, and this happens often enough that I can make this a point. All you want from this are the locations of zeros, which means any constants you can disregard because you're going to set it equal to 0. Kill the stupid constants. Be smart about this. When you plug in stuff into your variables, very often big chunks of your thing become constants. Kill them. Right? That's why, well, you have to have a factor.
Why don't you kill the
first, right?
3 and the -3?
I could have, I just didn't want to. Didn't really need to, right? Not it. I could have there, but I didn't really need to. It's just that here I didn't want to write this over again. Although I'm already wasting the time I didn't want to waste, but I didn't want to write this over again. There was no purpose. I could see my real problem right there. That's a constant. It's not going to bother me. The only way to make this 0 then is making y something. Yeah.
When x equals 1, the y equals -2, y equals -3.
Yeah, so when x is 1, which I got from here, if I plug a 1 into this, let me just write this out. I get 1 times -1 times 2y plus 3 equals 0. Right? Dividing by that, I get 2y equals -3, divided by 2, y is -3 halves. Just solve the equation. You plug in something from here into there, solve that equation. Okay, and this is just systems of equations. Once you know an answer from one, you plug it into the other one to find the other variable, right? Nothing new. And of course, there's no undefined places here. So that's my total list of critical points. What would be my next step now? And you can see how this quickly kind of starts to suck if you have a huge list of critical points, because the second derivative test is kind of large for each one of them, in a way. What's f(x)(x)? It's not too bad.
2 friend.
I like it. 2
y squared.
y plus 3. I like it. Or you can multiply it out.
Oh.
What's f(y)(y)?
3x.
Careful.
X squared minus
2 x times x minus 2. With me? Fyy, the only thing with the y in it is here, its derivative is 2 times the constant that's left. Okay. You guys with me on that? Let's look at that a little more specifically. Fy is x minus 2, 2y plus 3.
yeah.
So when I take the derivative of y again, the derivative of this is 2. This is a constant. There. All right, all right.
Okay.
And what's fxy?
0.
Careful.
2x minus
So take the
2.
derivative of y with this one, right? So that'll be y squared plus 3y. It'll be 2y plus 3, right?
Times
If you would have done fyx, that actually is
the same thing.
Comes out to be the same thing, yeah. It has to come out to be the same thing. So if I look at this again, actually I left out my 2. So fxy would be,
Paren.
let me write this out for us. It
2x
would be
minus
y
2.
squared plus 3y times 2x minus 2. Let me see if you guys are cool with this notation. Y,
Okay.
right? Because there's fx with respect to y now, and that's going to be
2y plus 3. 2x minus 2.
yeah times 2x minus 2. 11. Cool. Of course, you get the same thing because this is x squared minus 2x. If you do it with respect to x, you still get 2x minus 2 times 2y plus 3. Alright, so there's fxy. So we're just going to do one point. I think you guys can do the other ones. Because you got the list of what it means. And I will be actually nice enough to give you that D and what does it mean thing. For some reason, I did last semester, I should probably do it again this semester, right? So I'll give you this. Let me make sure you understand. I'll give you this on the test. It'll be sitting on the test. Damn straight. Yeah, you better like that. So D is fxx fyy minus fxy squared.
All of which equals.
So if you just pick a point, 0, 0 will be kind of boring a little bit because that's 0 for 0, 0. Looking at the critical point 0, 0. So if I look at 0, 0, I get 0 times 0 minus
Positive. No, negative 6.
negative 6 squared, right? So I get negative 36. That is, are you guys with me? That is less than 0, which means I have a saddle point. So 0, 0, whatever. I lost my function. 0, 0, 0. Right? If you plug 0 and 0 and you get 0, is a saddle point.
Professor,
Yes, sir.
why does fyx never come into
It does.
the equation?
fxy is equal to fyx for all functions that this theorem defines it's used for.
Just like
It's
that-
used for anything continuous on a disk around the point that you're interested in.
Just like ffx is equal to fy.
No, they're not equal. Careful. fxx is not equal to fyy. Certainly not. In fact, here's a good case for that. Right? But fxy is equal to fyx for functions that are continuous. That is true. We saw that way back when we first defined higher order partial derivatives. You can kind of prove it to yourself. I mean, we did fxy, but if we do fyx, isn't that going to be x squared minus 2x? So wouldn't that be 2x minus 2 times 2y plus 3, which is exactly what we got here?
I'm sorry, when I said ffx equals to fyy, that's just the sign, just positive or negative?
That's one of the possibilities.
Okay.
Right. So let's check one more point. 2, negative 3. Why not? So if we look at 2, negative 3, what do we see? What's fxx there? 2, negative 3. So y is negative 3. I get negative 6 times 0. That's not very interesting. Shoot. It doesn't matter what it is here, but this would be, yeah, 0 again. Yay. So you're guaranteed this is going to be what? Yeah, as long as fxy is not 0 itself, and is it? fxy at 2, negative 3 would be 2 times negative 3, negative 6. So again, that comes out to be negative 36 saddle point. Okay, yes ma'am.
To find the z, would you plug it into the very original equation?
Beautiful.
Okay.
And I don't know if you guys remember this, but a lot of times when students first learn these tests, they plug it back into the wrong function. If you want to know where your function is, what the output is, you have to go back to the original definition. Because if you plug it into f prime, you're going to get the slope, and all my students always told me, it's always at 0. Well, because you set your slope equal to 0, you can't plug the damn thing back in there, you know it's going to be 0. If you want to know where the point is, plug it into the function. Cool. Okay. So how we feel about that? You can see the critical point list can kind of get big easily. Yeah.
Yeah, I was curious how you made those critical points. You have like, you generated 3 points for the
Yeah,
first
these three
point. Yeah, I was-
directly came from this.
Yeah, I was curious how you know which ones go with the B equation, which A's go with the B. I mean, it's like.
You pick. I could have gotten the answers to this one and then plugged each one into there. How do you solve a system of equations? You solve for a variable and then you plug that back in to see what the other variable is. So since I got 3 options, I got to one at a time plug each one of them back in. Of course I'm going to plug it back in to the second dude. I got to use both pieces of information, right? Okay.
Our second cell point was 230.
Where are we at, sir?
The second cell point was
Oh, yeah.
230.
Because when you plug a 2 and a -3 in, yeah, you get 0. So 2, -3, 0 is another saddle point. This must be a very funky looking function. It's got at least 2 saddle points. It's got 4? I love it. Oh, is it one of those that look like an egg carton in a way? It comes like that in 4 different directions. Funkadelic. Okay. I am desperately trying to get to a certain point here, so we do have no time almost, but I want to go back to something that's going to lead us into the next section, and I'm going to desperately try to get as much in as I can, which I know you love it when we teachers do that. Remember this guy. Alright, this is just a few minutes ago we did this one. And we found, what did we find? Somebody remind me. We found it was 3, right? There was 1, -1, 3.
Yeah, local min.
Was a min.
Yeah.
That's the work we did before, right? Now, remember when you first learned about relative max and min, what was the other type of max and min?
Absolute.
Absolute. And absolute was kind of nice. No test required. You just plug the damn thing in. Whichever's biggest wins for that. Whichever's smallest wins for that. Right? I don't know if you guys remember that. Absolute was kind of nice. You also had to remember, though, to plug in what? Not just critical points, endpoints. So in this case, here's where it gets not so nice for multivariable. Our endpoints are not points. Our endpoints are some boundary of some region. Right? Because again, in this case, let's say we're restricting our inputs to be on this circle. Or not on it, let me say in it. You with me? So that's my allowable domain. That's what I can use for this function. So anything outside of there can't be answers. But to find the absolute max and min, I must somehow include looking at the boundary itself.
So it's just an arbitrary restraint head.
Well, sure. Hopefully in real life the constraint would come from not trying to kill somebody or whatever, not trying to overload your wire. You have your constraints in real life about how much load can this hold, how much amps can this thing take. That's where constraints come from in real life. This one is certainly arbitrary, just for right now, just to do that. So here's the funny thing. I've already done this. Now, does anybody have a suggestion? What's the boundary that I have to check? What is the boundary? It's a circle. So the boundary is actually all these points. Now, anytime I put a constraint on a function, I should be able to rewrite that function in a simpler form. Let me say that again. Anytime I put a constraint on a function, there probably is some other way to write that function in an easier form. So this is my constraint. For the boundary, I can only use points that are on that circle. Therefore, this should not be dependent on 2 variables anymore. Right? Whatever x is, it determines what y is. You with me? The book gives one method of how to do this, and that actually is to take it down to a theta parameter, since it's a circle. I'm going to give you another option. So you can look at the book. This is example Oh, which one? Oh, here we go. Example 6 in the book. Let's look if we see if we get the same answer they did in a different way, and what I consider an easier way. Because imagine if this was an ellipse. I can't even do a parametric equation for that. Not nicely, anyway. So, what does this become then if I use this in it? I can, for example, I can write this as x squared equals 4 minus y squared. Or x equals plus or minus square root of 4 minus y squared. You guys with me? Okay. So what does this function become then? What's x squared plus y squared? That's kind of nice. 4. It's 4. You with me? Don't overthink it. Don't look at here first. Look at there first. And that's a very quick substitution to make. And this is going to be a function of what now? Let me write this in a different y. I love it. So x squared plus y squared is 4 minus 2x. So that's plus or minus 2 square root of 4 minus y squared. Are you guys with me? Just substitution. Okay, sort of. I really want you guys to get this idea. We've actually kind of done this idea before. I can input points in any order I want to. In this case, I happen to want to put them from a circle. So I'm going to do that. I'm going to plug them in. I'm going to plug them in before I even know what they are. I'm not going to pick any specific ones. I'm going to plug all of them in at once and see what my function becomes on that circle. Let's see, where am I at?
Plus 2y.
Plus 2y plus 5. So how do you maximize that? Now we're back to math 1a, because I have one variable in there, right? It's not multivariable. No partials required, right? How do I maximize that or minimize that? Or
Find the derivative.
yeah, what's the derivative of this? This one's not too bad, hopefully. The plus or minus is nice, because that actually makes you, if you forgot your negative, you're still okay. Right, don't worry too much about the plus or minus. Just carry that with us. Let's see what happens. The 1/2 kills the 2. Becomes a negative 1/2, so now it's over this. The inside gets a turn, so it gets that on top. Right? The root of the inside will be negative 2y, but the plus or minus eats that up. Now it's the negative 1/2, so there's that. Yeah, sorry, I'm not done with that. Yeah, plus 2, and the 5 goes away.
Where'd you get that 4 plus or minus 2 roots?
So 4 is this.
Create like that legend on the side there.
2x, plug the x in. There's that. And there's 2y, and there's 5.
Okay.
Just plug your constraint into your function and see what you get. And then I want this equal to 0. So then the 2's die. Let me see if I can kind of get us to the punch here. Equals square root of 4 minus y squared. The plus or minus makes my negatives actually very easy to handle. Just forget about it, because the plus or minus eats them up.
What?
Yeah.
How do you get
What's
rid of
that?
both?
Subtract 1, multiply by this. It's plus or minus, so I can divide by the negative and it doesn't care. Subtract the 1, multiply this up, divide the negative over, and it's still plus or minus. All right, nothing amazing, okay? Square both sides. Add this over. I get y equals plus or minus root 2, right? Can you solve that? Yes, sir.
Can you go through the derivative real quick?
So this is to a 1/2 power.
Oh, there.
So the 1/2 comes down, kills the 2. That 2 is actually from the inside getting a turn, and that's the negative 1/2, so there's that on the bottom. Cool. Okay. So y equals plus or minus root 2. And if you look at example 6, that's what they got for y. How do I get x? Plug it in. And you get x is plus or minus root 2. And those are the points they actually look at.
So, why don't we use this method, like to turn the 2-variable function to a 1-variable function, and then we'll deal with why
You
does it
can't-
always.
Well, because in the earlier examples, I didn't have this constraint function, did I? Right? This is a new thing. I didn't have that earlier for doing the second derivative test and all that kind of stuff. I didn't have this to work with. There was no constraint on my input. It could be anything from the domain. Alright, so next time we're going to be talking about something that is used a lot in physics, but it's not that difficult. The math is really simple. The idea is actually really simple, finally, for once. We'll see if you believe me. And we'll do that next time, after the break. Have a good break.
Okay, why did you set root equal to 0? Because at the boundary point, it doesn't have to be 0 for the derivative for it to be a min or max, right?
On this boundary, I want to find where its max and min is.
Oh,
Yeah.
okay.
Now, if I would have time, you could actually define a boundary, for example, to be like this. In which case, it's a straight line, and when you have a straight line, you do have to check the endpoints, right? But this is a circle. I just want to find on that circle where is the max or min, and that'll be my candidate for the absolute max or the absolute min.
So we have to compare the x and y for that, to that, and see which one is.
Yeah, so far I got 3 is what I'm output.
Right.
So yeah, I got to see what outputs these give me, and it'll tell me which one's the min, which one's the max. I think this ends up being the min, absolute min, and then one of these is the absolute max.
That's what we're
I love it. So you got square root 2, negative square root 2, negative square root 2, plus and minus, minus.
Why don't we say FY?
Because they both mean the same thing. And again, if d is greater than 0, this must be positive. Which means these have to have the same sign. So me saying this is positive is the same as me saying this is positive. They just chose one and they chose the first letter they saw. But you're right. That's kind of like hidden behind it. There's no need to say it because this implies it. Cool.
No. I had a question on this graph. You talked about how this part B thing is supposed to be comparatively similar to.
Yep.
I got the right number this time around, it's still.
Seen better days.
Part B.
I don't know why he comes to class.
And I checked if it's a mark, would it explain the domain where
Took out 3 points on
for the
not spelling out.
like -1 plus 3 bits.
Yeah, I think I got that too.
4 bits. And everyone that's
Didn't
right.
you like
It's
that
still
one, that
not
class?
similar.
Well, now look at the difference here. How much did it change by? The derivative is all about change.
Yeah.
So from here to here, it increased by about 7 point something.
Yeah.
It was positive for one thing. It's not 5, but it's pretty close. Relatively close, because it turns out that this was actually kind of a big step to take. This minus 3/5, this here plus 3/5 minus 4/5. Turns out it was kind of a big step to take because as we're taking the step, my surface is doing something else. Right? Going up faster or slower than they thought. But it's still positive and on the same order as this. Some tests I made, this came up to 12.4, the difference came up to 12.8. I mean, that's pretty, close. But this one I think was the one that's the furthest, but it's still, this is 7 point something or other, and that's almost 5. They're both positive, so it is kind of a following of what that predicts, and it's not going to be perfect. It's not.
So then, like, for the answer you were looking for, when you say, does this illustrate what you found in part B, you can say that the difference between them
Is close to the prediction it's made.
Okay.
When you take a derivative at a point, in a way you can look at it as a prediction for what your function's going to do. Now, the minute you move from that point, the predictions change.
Yeah.
So that's why any large step I take could be off, possibly even way off from what my prediction is. Because my function could actually do this, and I'm going like this, I'm way off. So I try to make the function that wasn't too bad. I think that's the one that was the worst. But it's still positive. So it said you should increase, and you did, but it was predicting more of an increase than it was. If I remember. Yeah, predicting less of an increase than it was. So my function must have been like that. Right, I thought it was gonna go up higher than it did. Cool.
I lost you here. You took Fy or partial Y, what was F? What was Fx?
Good, that's right.
It used to be Fx, it's
Yeah, it
alright,
used to be.
it's alright. No, I still have it written down.
Yeah, this is it.
There's a 2x minus 2, yeah,
Yeah,
yeah.
I just multiply those in.
Yeah, so that gives you Fxy. Now I completely lost you from here to here because you need to square this to make it Fxy squared.
Yeah, but I would just plug in the value and then square it, you don't square it. For example, if I want to look at the critical point 0, 0, I plug a 0, 0 in.
How do you know?
Because you got your list of critical points.
Yeah, I was gonna say, which one do you choose?
All of them. Not once, obviously, but you have to do each one of them.
So oh, that's why the guy who got the 98. 'Cause
See, I mean, those are the.
he said there's 4 saddle points.
Those remember this here, greater than 0, less than 0, equal to 0. Right, that's the second derivative test for math 180.
Yeah.
What's that? Each critical point one at a time. So same thing we gotta do. We gotta take each critical point one at a time and apply this to it.
Okay, so you just chose one, two.
I didn't want to do all.
Okay, gotcha. That's
I
what
happened to choose two that came out to be saddle. I think some of them are names.
Okay.
But try that out with the other critical points. Plug it in here.
So you plugged in and you got 6.
So fxx at 0, 0 would be 0 times whatever. 0 times whatever. Both of those are 0. There, 0 times 0. And then like we just said, 3 times negative 2 is negative 6, and I have to square it.
0.
So that's why you don't square the function. Screw that.
Yeah.
I don't follow that out or whatever. Just get the number and then square that.
But you get the number by plugging
Definitely.
in
0, 0, so you get 3 times negative 2, negative 6.
Okay.
And
So
then square it.
so its critical value can be plugged into just about any of these guys.
It's gotta be. It's gotta be plugged into all these.
Okay. Okay.
To put that D together, you have to plug up the point that you're looking into all of those, and see what this whole thing comes out to be.
Okay.
Cool.
Sorry, looking here, Monday, so it's 2 3 different.
Oh, yeah. Oh. So, there's your test. Let me know if this makes sense. I'm trying to give you like your overall average. Cool.
Does that include the percentage? The average?
Yeah, all these here. It just doesn't include the whole.
Okay.
I give you a range of possible values if you turn in all the whole, turn in the whole. Yeah.
Okay, thank you.
Sure.
How did you know? Okay, that's right. You knew it was a saddle point because it's less.